Let us imagine to have a turbulent fluid flow, like a stormy wind. Let us now imagine to release a certain amount of tiny smoke particles, dust particles, and coarse salt grains. What happens? The smoke particles will move along chaotic paths, following the turbulent flow. Conversely, salt grains will drop vertically, insensitive to the air movement. Finally, dust particles will behave something in between. Why? Because the three types of particles are characterized by different particle response times, which can be defined as a measure of the time required by a particle to react to changes in the fluid flow. In order to shed light on this concept, let us consider a uniform flow with velocity capital U, and let us consider adding a solid particles, initially at rest. Of course, the particle will start moving. The movement of the particles is obtained by solving Newton's second law, that is, by imposing that the product of the particle mass mp and its acceleration, dv over dt, is equal to the forces exerted by the fluid on the particle. If only the drag force is considered, then the right-hand side of the equation becomes 1/2 times the density of the fluid ρf times the drag coefficient cd times the area of the particle cross-section, p times dp to the square divided by 4, times the absolute value of the relative fluid particle velocity, capital U minus v, times capital U minus v. Now, let's assume that the flow around the particle is in the Stokes regime, which means that the particle Reynolds number ρp, defined in terms of the particle diameter dp, the absolute value of the relative fluid particle velocity, the fluid density ρf, and the fluid viscosity μf is very small. It can be demonstrated that in this regime, the drag coefficient is equal to 24 divided by the particle Reynolds number. After some mathematical calculations, the particle equation of motion can be written as dv divided by dt equal to 1 divided by tau p times capital U minus v, where tau p is the particle response time in Stokes flow, which is equal to ρf times dp to the square divided by 18 times μf. Solution of the differential equation with the initial condition v at t equal to 0 yields v dt equal to capital U times 1 minus x of minus t divided by tau p. So the particle, initially at rest, approaches the fluid velocity, capital U, following an exponential law. The motion of the particle is affected by the particle response time, tau p. When tau p is small, then the particle velocity approaches the fluid velocity very rapidly. So the particle responds very quickly to the fluid. Conversely, when tau p is big, then the particle changes its velocity very slowly, thereby approaching the fluid velocity after a long time. So, referring to the initial example, the particle response time of the smoke particles is smaller than the response time of dust particles, which in turn is smaller than the particle response time of the coarse salt grains. However, the particle response time alone cannot fully explain the fluid dynamic behavior of the traveling particle. A more representative parameter is the particle Stokes number, a dimensionless number given by the ratio of the particle response time, tau p, and the characteristic timescale of the fluid flow, tau f. The meaning of the particle Stokes number is as follows. The numerator represents the time required by a particle to react to changes in the fluid flow. The denominator represents the time required for these changes in the fluid flow to occur. So, if a particle has a Stokes number much lower than 1, that means that the particle response time is much smaller than the fluid time scale. As a consequence, the particle reacts almost immediately to any change in the fluid flow velocity, and basically it follows the fluid. This is the case, for instance, of smoke particles flowing out from a chimney. At the opposite extreme, if a particle has Stokes number much higher than 1, it does not have any time to react to changes in the fluid flow, because they occur too quickly. As a consequence, the particle does not even feel the action of the fluid, and its motion is dominated by inertia and possibly mass forces such as gravity. An example of this situation is the movement of a cannonball. The problem is how to evaluate the characteristic timescale of the fluid flow, tau f, even more so because most of the particle-laden flows of engineering interest are turbulent, and it is well known that turbulent flows are characterized by several timescales. The timescales of the turbulent fluctuations, in fact, span between two extremes. The timescale of the largest eddies, which is the largest possible timescale, is called integral timescale, and it is referred to as tau capital lambda. The timescale of the smallest eddies, which is the smallest possible timescale, is called Kolmogorov timescale, and it is referred to as tau lambda. The existence of different timescales gives rise to different definitions of the particle Stokes number, which correspond to different physical behaviors. If the Stokes number is defined with respect to the integral timescale, that is STP capital lambda equal to tau p divided by tau capital lambda, then having STP capital lambda much higher than 1 means that the particle is weakly affected by any of the turbulent structures, including the largest ones. At the opposite extreme, the Stokes number can be defined also in terms of the Kolmogorov timescale, that is STP lambda equal to tau p divided by tau lambda. Particles having STP lambda much lower than 1 are strongly affected by all turbulent structures, including the smallest one. In practice, they follow the fluid, behaving like a passive scalar, such as when an ink drop is splashed in water.